In this demonstration, we're going to show the ice melting demo, and we have two cylindrical discs, relatively the same size, same proportions. We have about the same height in both of them, same diameter. However, if you notice, one possibly, if you're trying to make some observations, maybe one's a little shinier or more glossy, one's a little more less reflective or maybe matte. One has what looks like it could be little rings etched into it around, and they both do have a little seal. Basically, it's like a silicone seal or a little rubber seal, rubber gasket that you buy to, install to prevent things to leak. And so I'm gonna grab some ice, try to get an equal amount of ice for both, just to show some consistency. Just gotta pull out from my sample here. And we got a bigger piece. Apologize for the delay. I actually have a bunch of melted ice that I've been playing around with doing this demo throughout the day. Well, regardless, one's a little bit bigger than the other, but even with the one that's bigger, I want you to notice what happens. And so the one that was bigger, usually you would think if I had a bigger piece of ice, it might take longer to melt, and yet on this one cylinder, it's actually melting a lot faster. And so on the left, we have a material that obviously is not going to allow the ice to melt, but on the right, we do have one that allows that ice to melt. Now, in order for ice to melt, obviously energy has to go in to that object or into the ice in order for it to melt. So that means I have to have something that has the ability to conduct energy or to conduct heat. And so what often happens is in class, when students will ask about it, they will think that the one on the right is actually hot, or maybe that it's a hot plate and that it's warm and that will actually melt that ice. And in actuality, they're totally wrong. It's actually a lot colder when you remove the ice and the water from both and you feel how these actually feel. You feel that this one over here is actually colder. So I'm just gonna dump these, get rid of the ice. We'll throw it back down there. And again, we'll run it again. Maybe a smaller amount of ice this time. But as we put them on, again for perspective, put two brand new pieces on there. The one that is on the right side obviously is going to continue to melt faster. That's because the one on the right is actually a metal. The metal, as one of its main properties, has the ability to conduct heat. And so there's heat and energy coming from the table into the block and then into the ice, and then also from the air in the metal, or into the metal and then into the ice. And so the other one over here actually is an insulator. And it's some type of polymer material. There's a lot of air space in it, even though microscopically there's a lot of airspace. So kind of like styrofoam would have a lot of airspace and not allow that transfer of energy to come from the table in or from the air into the block and then to go. And so if you have a water bottle that will allow extended times with ice water in it, or a hot beverage, there's usually a vacuum seal that prevents, or maybe even styrofoam, the old types of thermoses, that would prevent energy going into the object and to warm it up. Like if you had ice water, or if you had a hot beverage, it would block the air or the energy from leaving and losing the heat. So it's a cool little demo to do, and those are called the ice melt blocks or ice melt demos. And again, the key thing is because the one on the right is actually a metal and has the ability to conduct the energy and to conduct the heat a lot better than the one on the left, which is more of an insulator. And so just to kind of show you an example, we'll clear these out for a second quick again and put it in a little perspective. We'll get that piece of ice off there. We'll see when I drop them, it doesn't make a lot of noise, but this one you can tell sounds like a metal.